In this section, we'll look at the fundamental theorem of calculus part 2, which is actually the part of the fundamental theorem of calculus we'll use most often. What it will allow us to do is use antiderivatives to calculate the value of an antiderivative. So we're plugging in constants to this a to b, and we're working out. What it's saying then is that if we know that we have some function f that is a general antiderivative of f of x, so we're taking that f, there is no plus a constant going on here. We just take an antiderivative of this, we plug in the upper limit of integration, b, and subtract the same function except that we're plugging in the lower limit, a. This is useful to us because before we had to calculate an integral by knowing the exact value of the area underneath the curve, or we had to estimate it using rectangles or Riemann sums. But now we're going to be able to do this exactly by using integrals. So as long as we know the antiderivative, we're going to be able to do it this way. So if I have this as my integral, what we need to know, first of all, is the antiderivative. I know the antiderivative of 3x squared would be x cubed, and the antiderivative of 1 is x. We don't worry about the plus c. And what I'm going to do is I'm going to put this in parentheses and write that we're going from -1 to 3. Now notice in my rule it doesn't have that step in it. That's just kind of an intermediate step to help us see what our antiderivative is. What our fundamental theorem actually tells us is if we use that antiderivative, we can first plug in the upper limit, the 3. So I have 3 cubed plus 3 as my first part, minus, and then we do the same thing again except plug in the lower limit. And adding that together we get 32. And so I know that this integral here would work out to 32. So again, here's what we did. Our correct notation, you could use this kind of bracket, writing our -1 to 3, or you can use parentheses and put a long line here and show that you're going from -1 to 3. And this just shows that you don't have an integral anymore, that you're going to plug these values in as you go. And then our next step will be plugging in the values, first doing our upper limit and then our lower limit. If we're asked to find total area, remember that the total area is different than finding the integral, because the integral is going to have positive and negative sections canceling each other out. And so we have to look at each part individually. To find this analytically, then I would need to go first from my a to c. In the next part I'm going from c to d, but that's the negative area there, so I'm going to make that minus, which will turn it into a positive. And then for the last part, then I could maybe add that because we're going from d to b. So anytime that we have the positive area, we'll just leave it. Anytime we have the negative area, we need to subtract it. And we'll need to integrate each one of these parts individually. It's saying that we're adding the absolute values here. So I could have also thought of this one as adding an absolute value, but by subtracting that value would do the same thing for me. So in this example, we're given a graph and we're asked to find the area rather than the integral. So I can't just, well, first I'll look at my graph and notice that if I'm going from 0 to 3, as it says, I have part of this that's positive and part of it that's negative. Now this one's actually set up pretty easily. We can see that our only 0 is at 2, which you could also check here by plugging that 2 in there. 4 minus 2 squared would be 0. So that's the only place where this is going to change. And so to calculate the integral, finding the area, we need two sections. The first section we can see from our graph is positive, and so we're going from 0 to 2 for our function. The second part is negative, so we need the absolute value of that, or we can subtract it, going from 2 to 3. Our next step then would be to take the antiderivative of this, which would give us 4x minus the x cubed, but it would be 1/3 times x cubed, and that's going from 0 to 2. The second part has the same antiderivative, but we still need to write it out again because we have different limits of integration. This time we're going from 2 to 3. We would then plug those values in. Plugging in the 2 would give me 4 times 2 minus 8 over 2, and then plugging in the 0 here on that same part would give me 0 minus 0. Okay, so that's just the first part there. Over here I'm going to plug in the 3 first, and then I need to subtract away the same thing, but now I'm plugging in the 2. And so it would look like this. So this whole first part minus that second part, doing all the work to simplify this is eventually going to come to 7 2/3. We can also use our calculator to do this, although the way the book is telling us to do it, it's kind of an older version. But we do this by taking the absolute value of the entire function. So when we write our function going from a to b, we would plug it in with our absolute value here. And what that's going to do, if we look back at this last graph, it would have turned all of our values positive. So the second part would have been bounced up here. The area we would have found if we had used absolute value would have been the area under this graph, not this down here. It would have flipped it back up. And so the absolute value is going to work to find the area, not the integral. So in this one here, we have x equals cosine of 2x. Now if we were going to do it like we did the previous example, we would have to find all of our zeros. Now it might not be easy to find some of the zeros here. Also, we're going to have a lot of intervals that we'll have to add, subtract, add, subtract. And it's going to be a lot of work to do that by hand. But using our calculator, if I plug this in as the integral going from -3 to 3, and I use the absolute value of x cosine of 2x dx, then that's going to change my graph so that everything will now be a positive value there. This area all above the axis. And notice if I plug this into my calculator, looking first at going from -3 to 3, I just plug the function straight in. It gives me a value of 0. If I want to plug it in to find the area, not the integral, then I'll go from -3 to 3, just like before, but then I'm going to take the absolute value. So you can just type in as ABS, and then type in your function. So times the cosine of 2x, and then that turns all of our values positive, and so we'll get a positive value for that integral. And so our integral, rather than canceling out and giving us a 0, it's actually going to give us the area between the graph and the axis. Here's another example. We want to remember in these problems that we can think about integrals as dealing with area here. Now first of all, as we read this, it says f is a continuous function over this domain where h is the function defined below. Now since this is an integral, it means we're taking the antiderivative of f, which means that h prime of x is equal to f of x. So the derivative of this would give us the inside here. We're first asked to find h of 1. Notice that that means we're plugging 1 in for x, which means we have an integral here going from 1 to 1. And so that's just going to have to be equal to 0. So we know that we're starting at, if we're here at 1, then our original function is at 0. Okay, the next question asks, is h of 0 positive or negative, and explain. We need to remember that when we have a function like this, when we're calculating an integral, what we're doing is we're accumulating area. If we think about adding, as we move from left to right, we're adding lots of little rectangles, we're adding the area as we go. So if I'm starting at 1 and moving to the right, I'm adding area, which means that my original function, h, has a value that's going up. So h is increasing on that interval there, okay, because I have positive area here starting at 1. If I move over into the next region, I'm now looking at negative area. So as I'm moving over in this section here, each of these rectangles is taking away from my value. So my h is now decreasing. We can think about it as if we had turned around and now our position is going in the negative direction. And that will continue to decrease as we move from left to right. Now we can think of this then, if I'm starting at 1, if x is 1, that my y is 0, that means I'm starting with the graph here at 1 where my position is 0 and then I'm going up, but then when I get to this point here, I'm now going down. This question though is asking what's happening at h of 0. Notice here we have positive area. If I started at 0, I would be going up. I'm increasing. So if I'm thinking here, to get from 0 to 1, I had to have gone up. But notice I'm going backwards here. And so if I had to go up from 0 to get to 1, and at 1 y is equal to 0, that means I must have a negative value back here. My h of 0 has to be negative, or we'll say less than 0. And the reason is because h increases on the whole interval from 0 to 1. The next question asks the value where h of x is a maximum. So they're looking for the x value where we have the greatest value. Now remember, we were starting here at x equals 1, y was equal to 0. And then we increased. And if we think before that, we were increasing to get to that point. So anything before that would be a less value, but then we're increasing until we get to 4. So that's going to be our maximum, because after that 4, our graph is now going down. So the maximum. The next question asks for the minimum value. Now we have two places to look at in this graph. Starting here at 1, we went backwards, and so we had to go down. If we're thinking of moving this way, we're actually going down a little bit, which means this side would be a minimum. But then we have also got this area down here. After we reach our maximum, we go down, and we keep going down until we get to 8. So we have a question, which one, 0 or 8, is the minimum? Well, we need to think about this in terms of area. If we look at this area here, we went up just a little bit. This is a very small area. So if we look at this area here, this red area where it's going up, and we compare it to how much it went down, this area where it went down is a lot more than the amount that it went up. This area here of going down is just a little bit. And so this is going to be a small change, whereas this green area, if we maybe try to overlap that red area with this, we can see that we're going down a lot more. This little blue area is less than that, showing us that this green area is decreasing a lot more than we've already increased. So the minimum value has to be here at x equals 8. The next question asks about points of inflection of a graph. The key to this question is remembering that h prime of x is equal to f of x. The derivative of this is equal to that. That means if we want the second derivative of this, because we're looking for points of inflection, we need to be looking at f prime of x. So we're looking for sign changes to get inflection points, sign changes of h double prime. And those sign changes are going to be happening where we're getting zeros. So here's one here. We're going down, then we're going up. So at x equals 1, that would be a point of inflection. Over here, that looks to be about at 3. It's going up, then down. So x equals 3 would be a point of inflection. The next one looks like it's maybe about 6, going down, then going up. So x equals 6 is a point of inflection for h.